welcome back to my channel. With great power it comes, yes, that's correct, a great heatsink. In today's video I will be speaking about this part of the computer, which is the power generation. So we'll see how we can generate the 5, 12 and minus 12 volts that the computer needs. It's gonna be quite a long video, but still I think you will like it. So let's get right to it. Well, we have here the schematic of the computer. As you can see, this schematic is pretty huge. So there's a lot of things in this computer. So my idea, as you know, is to explain everything that we have in here in the schematic. Today I will focus only on this small part, the part of the power. So this part here. So we'll see that this computer actually needs 3 voltages. So it needs the 5 volts, it needs minus 12 volts, and it needs plus 12 volts. So this schematic that you can see here is not from the maker of the computer. It's not from Panasonic. It was made by reverse engineering by this user that you can see here, who is Niga. So Niga is a Japanese user who's done a lot of things on the MSX. So this is the website. So I'm looking at the website, which actually shows things about the FS-A1. So as you can see here, there's things about the power connector. Here we can see the weird connector I was telling you the other day. And what else do we have? Many other things. Well, it's in Japanese, so or you know how to read Japanese or you translate it. This part here is something that I will tell you about later. So this is to generate the 5 volts and many other things. Here you can see, okay, these are the kind of things that I wouldn't dare to do, to solder. This is the MSX engine, so these micro connections there, this is something that I don't like to do, but some people are able to do this. And yeah, many other things. I don't know what is this. So OPLL expansion circuit, so nice. Yeah, things about electronics. Well, anyway, lots of things that you can find in the website of Niga. Among the many things he's done this, which is this schematic. This schematic, to me, this is pure gold. It's super good. So you have all the details of the computer, and it's a very good schematic. For example, here it is a capacitor. You have all the characteristics of the capacitors. He's even added the jumpers that you can see in the computer. All these jumpers are added. You have all the kind of transistors, the temperature of the capacitors. So you have everything here in this schematic. So it's very good. And we start from here. So this is the weird connector, which has 3 pins. So in one of them is ground. The other one, it's 9 volts DC, so continuous current, and most of the amps are here, so 1.2 amps. The other pin generates AC current, much higher, but not that many current. And right after the connector, we have the switch, so you can allow the current to go through or not. you turn on or off the computer. So from the connector we have 3 pins. One of them is ground, so voltage 0. The other one is 9 volts DC with a lot of amps compared to the AC, so this one can draw 1.2 amps. In practice there's not that much, but this is the maximum. And the other pin is driving AC current, much more volts but less amps. So after that you have the switch that you can use to turn on or off the computer. Then you have some filtering capacitors here, and the next thing that we find is this coil here, which is L4. Then I will show you some in the video how it looks like L4, but it's a pretty nice piece. The first question here would be why we have a coil in here. Well, let's explain how a coil works. Okay, the idea of a coil is that you can draw it like this. It looks like this in practice. It allows DC current to go through. Okay, if you have AC current, let's say like this, a high frequency, it is blocked. In practice, what happens is that it generates a magnetic field around, which is then reabsorbed and emitted like current. DC current goes through, AC current is blocked. In here, you might be thinking, okay, but we are supposed to have DC from here. Why this is going through the coil? Because if this is already DC, it should not have any effect. This is true. If you have some voltage in here, DC voltage, you will have the same voltage here. What's the point of adding this coil here? The point is that imagine that these are your 9 volts. Your 9 volts will be the same in here, but imagine that for some reason you have a peak here or going down. Typically goes up. This, which is a high frequency, will be blocked. So instead of going up, it will be like this. This will be blocked. Okay, that's why you put a coil in here. For the AC, it's kind of the same. This AC is not a high frequency. Actually, this AC looks like this, so it's a low frequency actually, like this. Well, depending on your country, this is 1/50 seconds or 1/50 or 1/60 seconds. This is not really a high frequency. The idea is that if instead of having a wave like this, you would have a wave which contains a high frequency component. Let's paint it like this. This ripple would be fixed and will be smoothed, will be removed. So that's why you're putting a coil in there. So after the coil, you have your DC without these undesirable peaks, and you have your filtered AC. This goes to two different places. It needs to generate 5 volts that you have here. Is to generate 5 volts. It needs to generate -12 and it needs to generate +12. So to do this, it uses 3 different parts. It's they are very differentiated. So this part here is generating the -12. This other part is generating the +12. and this other part, it is generating the plus 5 volts. So let's have a look at each of the parts. This part and this part are very classic. So it uses the very well-known uh, 7812 and 7912 to generate the two voltages, and the little bit special one is this one, the 5 volts one. Why? Normally, in most of the computers that you'll find, it uses a regulator which is the 7805 to generate the 5 volts. This one in particular is not using this, it's using this regulator, the M5236L. Why? I don't know. Well, it's their choice. It seems that they wanted to remove the power section of the regulator to separate it into a different transistor, a separate transistor, which is this Q3. To understand how it works, we have the data sheet of the regulator that you can find easily and download it. And this is it. So the regulator is this device with 3 legs, 1, 2, 3, and it is used with an external transistor, PNP transistor, which is actually this one. So how the thing works? It generates a tension which is of 1.232 volts, which is called the V reference tension. So this tension is generated internally in the circuit. Okay, it generates this reference by itself. Then what it does is it compares this reference with the tension at this point. Okay, this reference you cannot configure it, so it is always the same. It depends on the regulator. On the other hand, this tension here you can configure it. So you have this configuration with these two resistors. This configuration is called a voltage divider. This is the output. Okay, so this should be our 5 volts. Let's call this V out, VO. This is our reference. So this is V ref. And here we have the configuration of the divider, the voltage divider. So the way a voltage divider works is if you have two resistors like this is ground, and you have input voltage, which is let's call it VO. Okay, this is our output, VO. And here is actually this is the output of the divider, which is called Vref, and the resistors are R1, R2. Okay, there's a formula that you can write, which is Vref equals VO multiplied R1 plus R2. Here what we want to have is VO as, okay, we want to know what VO is. So actually VO equals Vref multiplied by the inverse of this, R1 plus R2 divided by R1. So this is equal to Vref, this is 1 plus R2 R1. Okay, this is what you have in here. Actually, this is what you have in here. So VO is equal to vref. Vref is here, which is always 1.26 multiplied by 1 plus R2 divided by R1. Here they are fixing R1 to this value. It is a reference value. You can change it, no problem. I mean, if it's in the datasheet is set to 4.3K, okay, you can use the same value to be safe. And what you configure is the value of R2 to get your value of output. This should be our 5 volts. So we want to have VO, our output, equals 5 volts. So this is it. So we can write the equation. Should be something like 5 VO equals the reference 1.26 1 plus this resistance. In the schematic is called I33. Okay, let's go to the schematic. In the schematic you'll see that it's these two resistors, the divider. So you have here the one about 4.3K, and we want to configure this one, the R33, to have the our desired 5 volts. So okay, so we were saying we want okay, let's apply this equation. So 5 equals Vref, so Vref is 1.26. So I'm just copying the equation. So I want to know which value I should put in R33 divided by 4.3K. So if I do like this, I have that R33 equals 5 divided 1.26 minus 1. This is multiplied by 4. This is 4, sorry, 0.3. If I do like this, this equals to 12.76 kilo ohms. This should be the value of the resistor that I need to put in here in order to have here VO equals 5 volts. So it's 12.76. So let's have a look in the schematic. In the schematic, I have, well, it's not 12. We computed 12.76. I guess this value, okay, this value would be really complicated to find as a resistor itself. So they approximated to the closest value, so 13K ohms. Okay, so why do we need this transistor in here? It is related to the way this regulator works. So normally in a linear regulator like 7805, inside the circuit you have the part which controls the tension or the current, and actually you have a driver for it, which is able to pass a lot of current from the input to the output. This component here generates a lot of heat, okay, because a lot of current is going through. The part of the control, not that much, okay, so this is low tensions, low currents in here. So I guess the idea of the designers of this circuit was to separate the two parts. So on one hand to have a control here, and on the other hand have a driver in here. So they separated. So how this works? Okay, this is used like this controls the amount of current which goes from here to here. So we have our current, which starts here, goes up, goes this way, and also goes through the base of the transistor and comes here. Okay, the amount of current that goes this way is controlled by the amount of current that goes the other way. So this regulator, the control part, what is doing is to compare the reference with the tension that you have configured with the divider, and will allow more or less current go through its input. So the more current it drains, the more current you'll have here. It changes the current that goes to the input. So yes, it's not that complicated. The only interesting or different part is that you have these components which are separating the control and the driver parts of the regulation. Then we have the other part in here, which is the generation of the minus 12 and plus 12 volts. So how it works? Okay, here the difference is that we start with AC current. So this looks like this. So we have a positive part, a sinusoid, then a negative part, and this repeats. Okay, this repeats. And the first thing that we find in here is those two diodes. Why do we have these two diodes? Here it is to separate the positive parts from the negative ones. So this diode will allow only the current to go through when the tension is positive. It will also allow this to go through. This other diode, which is blocking, okay, so will allow only negative current to go through. So these parts here, the negative ones. So in practice, what will happen if we measure the tension in here, we'll see that it should look like this. Okay, positive, negative is at 0, positive again, then 0, positive, 0, and so on. So this is what we would be measuring at this point. And similarly, if we measure the tension at this point here, what we would observe is something like this. So negative, then 0, negative, 0, negative. Okay, something like this. Okay, so each of the parts will receive the tension that it needs. Okay, for the positive part, will have positive tension. For the negative part, which is here, will have negative tension. Okay, this regulator is very typical. So we can paint it like this: 28, 12. 3 terminals. Normally you connect one terminal to ground. You have your input and you have your output. The input is the non-regulated input. Okay, so the first thing that we find after the diode, which is here, we measure the tension in here. So we said that we should observe something like this, because the diode is blocking the negative part. A signal like this, we cannot put it directly into the regulator. So what we need is to move from this to something like maybe with some ripple, but something more horizontal, let's say, more DC. We need to move from this AC to DC. So the way that you do it is you can put a capacitor, which is actually this capacitor here, a large capacitor. So if you put the capacitor like this, what will happen is that the capacitor will charge, okay, up to the maximum, and then it will discharge slowly like this, okay. Then when the tension is over this point, we'll charge again, and then we'll discharge like this. Then charges, it discharges. So it will give us a shape like this, okay, which is not a bad approximation of a DC signal. It has some ripple, but it's fine. This goes through the regulator, and this regulator is okay. Let's draw the regulator. Is a very classic one. So in this case, this is 7812. Okay, this goes here, and you have your output, and the regulator does its magic and will output a signal, which is this one. This is 0, and in this case will be 12 volts. Actually, it's not magic. So if we have over tension in here, use its drivers to split the current. One will be used to generate this 12 volts, and the rest of the current will be sent to ground via some resistors, and it will generate heat, which is not good, but it is the way these linear regulators work. The good news is that we'll have a very stable 12 volt output. This is what we want. Then what other interesting things we have here? So we have seen the diode, and in the output we have these two capacitors. So this is again to stabilize the output. So normally this is our output. This is now our regulated output. So this is 0. This is 12 volts. And normally this should be like this. Why are we putting these capacitors in here? So the idea is that if we don't put these capacitors, and if for some reason we don't have enough current or enough voltage here, if this happens, this will go down, or imagine that it goes to 0, so it will go down, okay, and when it recovers, we'll have again our 12 volts. We don't want this, so we put this capacitor to do it is the same technique, it is the same idea. So instead of going to 0, here the capacitor charges, and here it will discharge like this. Okay, so we'll have instead of having an output like this, we'll have an output which is like this. It will go down a little bit, and okay, will be always close to 12 volts. Of course, if the cut is very long, you cannot make miracles. You won't have your 12 volts, but if it's something short, you'll have very little deviation, but you will be close to your 12 volts. And you can see here that we have a big one and we have a small one in parallel. You might be thinking why we are doing this, why we don't just put a big one there and that's it. And the reason is that this capacitor in here, the small one, is used to filter high frequencies. So again, when you have your signal like this with a drop, so you have your capacitor that will discharge like this, and then will charge again. These variations, these high frequencies, you don't want them. So if you put this small ceramic capacitor between ground and output, these variations will go through the capacitor to ground. So instead of something that goes like this, you'll have something that goes like this. So it's just to stabilize the signal. And that's it. From here you have your 12 volts positive master, which is the tension that will be used by the rest of the board, at least the parts that need the 12 volts. The minus 12 is kind of the same, so it's yeah, it is the same, but with a negative voltage. So yeah, you have this one that will filter the ripple. Here you can see that the plus sign, it's on the other side, because here it's a negative tension that we have in here. So you need to reverse the polarity of this capacitor. And yeah, it's kind of the same. So you have a large capacitor here, a small one to stabilize, and finally you have your minus 12 volts. That's it. So this is the way the power generation works. Things that we could improve in here, well, not much. It works fine. Something that I find a little bit worrisome is this capacitor. Why? Because if you look at here, you'll see that it's rated at 6.3 volts, which is fine. So this is over the 5 volts that we need. Okay, this will work, but we have a little problem, is that when this starts, this capacitor is not charged, so it will charge quickly, like this, okay? Then will remain charged. This is a lot of current, and this driver is able to drive a lot of current like this to here. This is a problem. More or less, if the machine was new, I would say, yeah, it's fine, you are over 5 volts in here, there's no problem. This machine is close to have 40 years. It's yeah, 40 years old, almost. And yeah, things are not that perfect, and this is a little bit problematic. So there's a lot of stress at this capacitor. Yeah, of course, the machine was not designed to be still working after 40 years. But anyway, we want that this machine works for many years still from now on. And well, something that we can do is to replace this capacitor and put one with more voltage. So just to reduce the stress into the capacitor. So here we could put, I don't know, 15 volts or maybe 50 volts. For sure, I will replace this capacitor. I will replace also this other capacitor. Where is it? A large one. Yeah, this capacitor in here. Okay, this capacitor is a very large capacitor. 4700 microfarads, and yeah, the rating is good, 16 volts. The DC goes directly through it, and it's a lot of stress in this capacitor. It doesn't mean that at this moment it's not working. It's working perfectly, but after 40 years, I would say it's better to change it. Actually, I will change as many capacitors as I can in this board. So there's no reason not to change them. So I will be changing them. Maybe the capacitors, electrolytic capacitors, of course, not every capacitor, because these capacitors can leak the electrolyte into the board, and this is something that you don't want at all that happens, because this electrolyte is very corrosive and can actually destroy your board. I'm looking for the small board that is used for video conversion. Yeah, this is the board. This is the board which generates the RGB and other video signals with the drivers and so on. So it's a board, a mini board, which is soldered into the PCB. And yes, it has some electrolytic capacitors. Yeah, this is an electrolytic one. Those are electrolytic capacitors. I don't think I will change them. I should, but if I want to remove or change these capacitors, I need to desolder this board, which is not complicated. The current which goes in here is low. Okay, this is just to generate the video output. So these capacitors were not under a lot of stress. So I think it should be fine if we don't replace them. So I don't think I will replace the capacitors in here, but I will replace every other capacitor. Let's have a look now at the components on the board. So here you have this gorgeous coil L4, pretty nice. On the right you have the regulator that we are using to obtain the 5 volts, and right here the big PNP transistor which works along the regulator and where most of the current goes through in the 5 volt rail. Now I have it without the heatsink, which is pretty bad because I cannot turn the computer for long, but it's okay for very short tests. Here we can see the 7912 regulator, and here we can see the positive one, the 7812 regulator. Wow, it is amazing that you're still here after this long video. For the next video, I will be changing capacitors, so I have bought a couple of them. And I will be putting back the heatsink because otherwise the computer will burn quickly. So thank you very much for watching. See you in the next video. Bye bye.